Okay, welcome to another live session for the Astronomy MOOC. I'm ready to take your questions on any subject.
Okay, so the first question is from Jake, who is on with us live, who asks, is faster than light communications a possibility?
Not according to standard laws of physics. So early in the last century, Einstein's special theory of relativity, which along the way showed that there's an equivalence between mass and energy, the famous E equals mc squared, also as a postulate had that the speed of light was constant to all observers and was an ultimate limit. So that's a postulate of a theory, and if we want to know whether faster than light travel or communication is possible, we have to do the experiment. So what we find is that electromagnetic radiation travels at 300,000 kilometers per second, the speed of light, or any other electromagnetic wave. And any physical object that we try to make go faster than that, we run into a brick wall. Essentially, if you take a subatomic particle, as high-energy physicists do all the time, and put energy into it to try and increase its speed, as it will approach the speed of light, and at CERN, the Large Hadron Collider routinely has particles going at 99.9999959, I think, percent of the speed of light, but they never reach C nor exceed it, because as the energy is actually put into the particle, according to relativity, the mass of that particle at a very high speed increases. So that's the physical nature of the limit of the speed of light. That if you try to make an object go that speed, or even approach that speed asymptotically, all you're doing is putting energy into the mass of that object, increasing its mass, therefore increasing its inertia, which is its resistance to any change of its motion. So that's what's been observed for a century. It's very secure. The hypothetical idea of tachyons or faster than light particles, there are some non-standard physical theories that predict tachyons or include them as part of their construct, but they've never been observed. So that's basically a pretty clear statement that it is an absolute limit. However, the sort of intriguing aspect of quantum mechanics or quantum behavior that doesn't necessarily violate that idea, but is still a puzzle within standard physics framework, is the idea of quantum entanglement or simultaneity. Einstein derided this in his day as spooky action at a distance, the idea that the physical state of two quantum entangled particles could somehow change, could depend on each other, essentially changing instantaneously over macroscopic distances. Entanglement's now been demonstrated over transcontinental, essentially Earth-sized distances, where a light signal would, propagate with an easily measurable time delay, and it does appear to be true simultaneity. So that is a puzzle. That is part of quantum mechanics. That's part of the quantum behavior of the world as we observe it. It doesn't necessarily violate causality or violate special relativity. Special relativity seems to hold, but I would say that it's the one unexplained part of routinely measured physics which raises a little interesting issue regarding the speed of light as an absolute limit.
All right, the next question is also from Jake, who is on with us live. And Jake asks, what is the importance of OSIRISRex to humanity?
Great question, Jake, because of course we just launched OSIRISRex. I use the we in the generic sense because University of Arizona is the first mission of its size and scale that a university has been fully responsible for everything except the launch. Also, that was true of the Phoenix Mars mission about a decade ago. The University of Arizona hosted and ran that mission. OSIRISRex, when you add in all the various bits and pieces and subcontracts, is essentially a $1 billion mission to visit a near-Earth asteroid, Bennu, and bring back a small sample, returning it to the Earth in the fall of 2023. The launch last week went off flawlessly, and so the spacecraft is on its way. The importance of Bennu, the importance of OSIRISRex, is that Bennu probably represents primordial material from the formation of the solar system. It is now in a sort of inner solar system, or almost near Earth or Earth intersecting orbit, but it started its life 4.5 billion years ago when the solar system formed as essentially primordial material from which the solar system, the planets, and the sun all formed. So it's pre-existing microscopic grains that tell us essentially how solar systems form. So by bringing back a pristine sample to the Earth, OSIRIS-Rex will hopefully tell us about the nature of solar system formation. There's evidence that solar systems don't just form in neat zones where there are terrestrial planets in the inner zones and gas giants in the outer zones. There seems to be some serious mixing of material early in the history, and that shows up in terms of heating and cooling. So by looking at the mineral grains essentially in this sample, we'll be able to talk about the heating and cooling history of this rock and therefore of the solar nebula itself. That's a lot of extrapolation to do that from a sample that might be as little as 60 grams. The OSIRIS-Rex mission guidelines called for somewhere between 60 grams and 300 grams. It could physically have more than that, but the apparatus to trap the dust can't ingest too much material. So too much would almost be as bad as too little. This sample will also tell us about the presence of organic materials. So we're interested in how life got started on the Earth and potentially in other places in the solar system. And we think it was seeded with organic materials that could include fairly complex molecules, simple amino acids, basic fats, sugars, carbohydrates, simple molecules, maybe a few dozen atoms, but the ingredients of life. And so obviously enormous attention will be paid to the most complex molecules that this sample contained. Another issue of interest is how much water this object contains. Water in the solar system, how it got there, how it's dependent on terrestrial type situations, and how much there is in general when the solar system formed is of interest. And even though Bennu may well radiation and the arid environment of deep space over 4.5 billion years, the minerals will show evidence of hydration or evidence of previous water bonding. And so the water content of the rocks will also be of interest. So all of those things can eventually be learned from really a very tiny sample indeed, just possibly as little as 60 grams.
All right, changing topics a bit. Ilsa, who is on with us live, asks, why does the moon always show the same face or side to the Earth? And is the lack of spin because the object is a moon rather than a planet?
It's a good question. This phenomenon is called tidal locking. So in general, when a moon of a planet or a planet orbiting a star is relatively small and relatively far from the object it orbits, it has its own rotation. So the sun spins about once a day. The Earth spins once a day, but of course it spins once a day while moving around the sun 365 times its spin. So the Earth is always changing its face towards the sun on a daily cycle, and the planets of the solar system are that way. However, when you have an object that is fairly close to the gravitating object that it orbits, then a phenomenon called tidal locking can happen. Tidal locking is associated with the tides themselves, and tidal force is essentially the difference in gravity between the near and the far side of an object. So obviously, if you take the Earth and the Sun as an example, the Earth is 150 million kilometers from the Sun, and the difference in the distance of the near side of the Earth and the far side of the Earth relative to the Earth-Sun distance is tiny. It's a tiny fraction of a percent, millionths of a percent. So there's really not much difference between the force of the Sun on the near side of the Earth and the far side of the Earth. But when you have an object like the Moon, which is fairly close to the Earth, and is also a fairly large satellite of the Earth, then the difference in the pull on one side of the Earth from one side of the Moon and the far side of the Moon is significant. That tidal force causes stretching of the Moon, causes stretching of the Earth, and that coupling due to the tidal force is what, in this situation of the Moon and the Earth, causes the Moon to essentially lock in a situation where that same side faces the Earth. And so we always see that side of the Moon, even as it orbits the Earth, and even as the Earth-Moon system orbits the Sun. And the far side of the Moon is always invisible to us, and has only, of course, been seen by a small number of Apollo astronauts directly. Now, that same phenomena can occur elsewhere, where there is a fairly large moon next to a planet and not too far away from it. So tidal locking is a phenomenon that we know occurs in the universe. We found a number of exoplanets, for instance, in the last few years, where the planets are like hot Jupiters. They're very tight. They're large planets on very tight, close orbits of their stars, and they are tidally locked too. So those exoplanets always point one face towards their star. And as far as an exoplanet goes, that actually reduces the odds of habitability when one side of the planet is being baked continuously by the star and the other side is essentially in the deep freeze pointing out into deep space.
All right, the next question is, while we are all taking steps to find an extraterrestrial place that can be habitable in the future, do you think we could make this possible on the Moon, Mars, or one of the asteroids?
Certainly, we clearly have the technology to create habitable conditions on extraterrestrial bodies, even if they're in principle uninhabitable. I mean, we just do that by technology. So there's sort of two sides to this question. One is whether habitable locations exist independent of our intervention, and the answer to that is probably on Mars, and on the Moon, probably not. The Moon is just a dry, baked, low-gravity body with no geological activity. And although there is ice in the lunar regolith, the cosmic ray hits on the surface, of course, sterilize the surface dust layer, and there's no liquid available water, basically. The water that might exist underneath the Moon's surface is in frozen form. So the Moon has some of the ingredients we might need to make a habitable situation, but there's no habitable part of the Moon. That changes completely when you get to Mars, an object which is also, on the face of it, fairly dry, fairly barren, fairly arid, very, very thin atmosphere, less than 1% of the Earth's atmospheric pressure, and pure CO2. That's the surface, and so the surface of Mars is similarly blasted by cosmic rays and UV radiation, sterilized to within a few centimeters of the top surface. No water can exist on the surface. There's frozen water and frozen carbon dioxide mixed into the Martian soil. But below the surface, there's completely the possibility for a habitable situation, and it doesn't have to be that far down. The best modeling and evidence indirectly from eruptions, some episodic eruptions of liquid water on the surface of Mars, is that at distances below the surface of tens of meters, maybe 10, 20, 50 to 100 meters, we don't actually know, there are subsurface aquifers, not everywhere on Mars, but in some locations. And with that amount of depth under the surface, the combination of pressure from the rock on top and mild radioactive heating from the rock below is sufficient to create the conditions where liquid water can exist. So that ice that sits there under the Martian surface will take a liquid form. So there's very good speculation, very well supported by indirect evidence, that Mars has habitable spots within the planet and near the surface of the planet. So that's the naturally occurring habitability. If you're talking about artificially created habitability, that's not that hard to do. All we need to do is create a bubble dome, sort of a hardened shell, which was obviously had some protection against cosmic rays and micrometeorite hits, and then fill it with a breathable air. And that air, of course, can be obtained in large part from the soil itself, because we can liberate oxygen by simple chemical reactions from either the Mars or the lunar soil and breathe that oxygen, mixing it with a buffer gas like nitrogen. And that same soil also contains liquid water, or water that can be liquefied. In round numbers, a cubic meter of either the Martian or the lunar regolith. It's not the same everywhere, but on average, a cubic meter, which is about a ton of soil, contains about 1 liter of water that you can liberate by a similar chemical reaction. So soil on the Moon or Mars, as arid and desert-like as those bodies are, in principle, simple technologies can be used to create water to drink and grow crops, if you like, hydroponically, oxygen to mix with another gas to breathe, and you can even use fairly simple electric techniques to turn the lunar or Martian soil into slump block and cover your habitat with it, and so make it a battle-hardened shell that would protect you from cosmic rays and meteorite impacts. So we can make either of those bodies habitable for small numbers of people without that much difficulty.
All right, the next question is from Sana, who is on with us live, who asks, we know that objects in space attract to each other. I think she means gravitationally. But in physics, there's always the positive and negative. So is there a force that makes two objects in space repel?
Not, unless they're electrically charged, of course. If you have electrostatic, physical objects can have an electric charge, of course. Matter is generally electrically neutral because they're the same number of protons as there are electrons in stable atoms. And so, on average, an individual atom is electrically neutral, and a large number of atoms is electrically neutral. So the average lump of stuff in space or in astronomy does not have an electric charge. It can gain an electric charge. There are ways to make matter have a net electric charge, and electrostatic forces are familiar on the Earth. If you rub a balloon on your hair or use various methods, you can put electrical charge on a physical object. And then it will follow the electrical laws of repulsion and attraction, depending on whether it's positively or negatively charged. But those forces essentially don't exist naturally out in space, because astronomical objects of every size, from a pebble or a dust grain in space up to a moon or a planet or a star, do not have a net electric charge. So we don't see those electrical forces tending to operate except within a solid rocky body. Gravity is a universal attractive force, and as far as we know, it's the weakest force but has a long-range interaction responsible for creating the structure in the universe. As far as we know, it has no opposite, with the bizarre exception, of course, of this entity that was discovered by astronomers in 1995 called dark energy. So where we anticipated the universal the universal expansion discovered by Hubble in 1929 should be slowing down because of all the matter in the universe. Matter tugging on matter will essentially slow down whatever expansion the universe started with. What was found in 1995 was the opposite, that the objects in the universe, the galaxies, were actually receding from each other faster and faster. And the agent of this accelerated expansion is something called dark energy, which does have the properties of sort of anti-gravity, if you like. It has a negative pressure. It exerts a universal cosmic repulsive force that is essentially driving space-time into an accelerated expansion. It is not physically understood at this point. So it's artificial, and it's kind of cartoonish to call it anti-gravity. It's not really a force like gravity at all. It just has this very strange character of universal repulsion as opposed to attraction. And the simple truth at the moment is that we don't understand what it is physically.
All right, the next question is from Kevin, who sent a question in via email, and it is, there have been mentions in the press about a proposed EM drive that may not be quite as dead as previously thought. Do you have any thoughts on this or know anything more about that?
Well, there are a set of propulsion. I'm not sure about this particular reference. Electromagnetic propulsion is one of the basket of ideas that are out there for doing better than chemical rockets. So all the rockets that we've ever seen, and all the ones even you're hearing about now with SpaceX and Blue Origins, are chemical rockets. Their fuel is really the same as rocket fuel has always been. At this point, it's essentially a very combustible mixture of kerosene, sort of like high-grade rocket fuel or aviation fuel, and liquid oxygen. It's a big chemical explosive, essentially. And the efficiency of chemical energy is, of course, really low. So there's been ideas to make various propulsion systems for rockets to move us around the solar system, and especially beyond the solar system, which will require something much more efficient than chemical energy. And EM rockets, or electromagnetic propulsion, is one way of doing it. One version of EM propulsion has been used on the Earth in various ways. There are rocket sleds. The military has had methods of launching ballistic shells into Earth orbit, which essentially just use pulsed electromagnetic fields to accelerate a payload along rails, just to guide the object, and then it flies off the end. That's been used for maglev type trains to reach speeds of 250 up to 300 miles an hour. So it's been used as a propulsion idea for normal propulsion for mass transit that we might take one day in the future. It's also been used, as I mentioned, by the military to launch payloads the acceleration to get to an escape velocity with like a rocket sled or a sort of space gun using electromagnetic propulsion, the g-forces are phenomenal to do this. And the big drawback for the EM type systems is that they are extremely efficient. Their acceleration and g-forces are phenomenal, but they would preclude sending any human payload or any human target. Rockets are much gentler. So these are ways you could launch nanosats or small satellites, or nanobots or whatever you want that's small and robust, but you'll never be able to launch human payloads by this method. Now, if you were in Earth orbit already, the hard part, of course, is getting into Earth orbit. If you're in an Earth orbit already, then gentler versions of these EM systems, electromagnetic pulses, is a nice way of getting you up to a high speed to explore the solar system and potentially beyond. But there are no prototypes of systems like that. So I would say that there's interest in these systems. The physics behind them is pretty well understood. There are no killer or showstopper technologies in the way of us doing this. But the R&D to get something like that going, especially in Earth orbit, would be hundreds of millions, probably billions of dollars.
All right, the next question is from Mustafa, who's on with us live, and I believe it's a question about one of our course videos where you talk about it being difficult for us to look at our calendar and predict when Ramadan is or any of the Islamic festivals. Is it hard or is it impossible? Can we match two calendars ahead of time?
Yeah, I don't remember the wording I used in the course, but I shouldn't have said it's impossible. It's just difficult. It's not information we can keep in our head. Those of us in countries using the Western, essentially the Roman calendar, are sort of familiar with the pattern of the number of days in the month and the leap year pattern and so on. The real distinction between the calendars used by the sort of Western and European world and the Islamic world is the difference between a solar calendar and a lunar calendar. So a lunar calendar is trying to match the 28.5-day orbital period of the moon as seen from the Earth, and the solar calendar is trying to match the 365.25-day orbit of the sun of the Earth. And those numbers don't go into each other very well, and that's really the fundamental reason why matching the calendars is hard. That they are not they don't have common factors, if you like, or they're not uniformly divisible. I think you actually have to go to time steps that are about 55 or 60 years before you get a ratio of whole numbers of lunar months and a solar year divided into days. So that's really the operational problem. That you're using two incommensurate counting systems for time, one based on the moon's orbit of the Earth and the other based on the Earth's orbit of the sun. And they are not neatly divisible, and so the calendars simply don't sync up very much. But on average, we can say what happens because the lunar calendar essentially shifts by about 11, I think it's 11 degree days per year through the solar calendar. And so every 30 or so years, the Islamic lunar-based calendar shifts an entire cycle through the solar year, through our calendar. And so predicting when the Hajj is, predicting when the main Ramadan, when the main festivals of the Islamic calendar are, is a little difficult. You actually have to have the two calendars sitting in front of you to predict when they will actually occur.
All right, the next question is from Jake, who is on with us live, who asks, do greenhouse gases in our atmosphere negatively affect radio telescopes?
Yes, in a sense. It depends on what the radio telescope is doing. So first of all, what are the greenhouse gases? And these, of course, are typically the heat-trapping gases. They're the ones that interact with incoming solar radiation and degrade it to infrared wavelengths or longer wavelengths, and so that therefore gets trapped in the atmosphere and heats it up, and then eventually the radiation leaks off into deep space. So we're talking about gases that essentially degrade visible light into infrared radiation or heat. The primary gases, of course, are carbon monoxide and methane. Methane, molecule per molecule, is actually a 30 times more efficient greenhouse gas than carbon dioxide, but it's even rarer. It's more than a factor of 30 rarer than CO2. So most of the greenhouse heating and greenhouse effect in our atmosphere comes from CO2. Water is also considered, it's not a gas, of course, but water vapor has the greenhouse property where it traps radiation. So of those gases, they're not generally a problem for radio astronomy at more than a centimeter wavelengths. So the kind of radio astronomy that's done by the Very Large Array, or especially the Arecibo dish down in Puerto Rico, those are typically a few centimeters up to tens of centimeters. Those waves essentially don't see the molecules of carbon dioxide or methane, and they don't really even see water vapor that much. So that kind of radio astronomy is completely immune from those gases. But that changes once you go down to millimeter wavelengths, or especially sub-millimeter wavelengths. That's heading to the boundary to far infrared, between radio and far infrared. So at the very short radio wavelengths, you're in a part of the electromagnetic spectrum where some of those molecules have transitions. Essentially, the low energy vibrational and rotational states of carbon dioxide or methane, and certainly water vapor, lie in a place in the spectrum where you're trying to do radio astronomy, which means that those molecules are going to absorb that millimeter radiation at the suitable wavelengths. And so the spectrum that you might see from space is badly eaten up or chopped away at the transitions corresponding to those molecules. So it does make a problem. Those molecules, and water vapor the most of all, make a real problem with doing millimeter and sub-millimeter astronomy. But at centimeter or beyond wavelengths, radio astronomy is really unaffected.
All right, the next question is from someone who is on with us live. Considering that we believe that a strong greenhouse effect led to Venus's very high temperatures and CO2 atmosphere, would it be possible to terraform it and reverse that effect?
Yeah, interesting speculation. The fascinating sort of fact that was told to me by planetary scientists some years ago that I sort of keep in my head, remembering that Venus is really our twin planet. It's within 5%, I think, of the mass of the Earth, so it's really similar to the Earth, much more similar to the Earth than Mars is. The other interesting number that I heard about Venus is that the total CO2 inventory on Venus is also similar to that of the Earth. Maybe not quite within 10%, but pretty close. And the difference is that on Venus, due to the greenhouse effect and the heating and the loss of any water vapor that might have existed on the surface 3 billion years ago, and the baking of CO2 out of rock, that CO2 is now in the atmosphere, this thick, choking atmosphere that raises temperatures to incredible levels. On the Earth, that carbon dioxide level is very modest because a lot of that carbon dioxide is bound up in rocks, or typically sedimentary rocks, of course, you know, chalk, limestone, things like that, carbonates, and also is dissolved in seawater. The oceans of the Earth in generally are not neutral pH, they're mildly acidic, and that's because of the CO2 from the atmosphere dissolves into the oceans of the Earth. So that's an intriguing fact, that on the Earth there's a lot of CO2 there, but in Venus it's all gone into the atmosphere. So if you were going to reverse, it's really hard to imagine how you can reverse that, because somehow you'd have to recreate the liquid ocean to possibly dissolve that CO2 out of the Venusian atmosphere. But you're already way too hot for liquid water to exist, so you have a sort of chicken and egg problem. And really, I've never heard anyone suggest the possibility of terraforming Venus, which is to say make Venus habitable, because it's essentially gone down a one-way road that it's very hard to reverse engineer. Mars, on the other hand, is in a situation where it's at the other extreme. It's too cold, and there's not much carbon dioxide. So there, if you take it forward, heat it up a bit, liberate carbon dioxide into the atmosphere and create a greenhouse effect, you could create the conditions whereby liquid water could exist on the surface of Mars where it can't currently. So Venus is probably not terraformable, even in principle. It's just impossible to go back down that road. But Mars could be terraformed if you take it forward towards higher temperatures, more greenhouse gases, and the presence of liquid water under a thicker atmosphere.
The next question is from Tom, who is on with us live. If a unified field theory was intended to combine quantum mechanics with general relativity, But doesn't a black hole violate the theories of general relativity? And shouldn't a unified field theory also include the behavior inside a black hole?
Absolutely. So that's a good question. The quest for a unified theory of the four forces of nature is sort of unfinished business, but probably the biggest unfinished business in physics at this point. So the underlying issue, of course, is that from the 20th century, physics had two great theories that were and have always been wonderfully confirmed by experiment, and they're magnificent sort of theoretical constructs in their own right. One is general relativity, the theory of gravity, which is a geometric theory of gravity involving curved space-time. The other is the theory of the very small microscopic subatomic particles. That's the quantum theory. And these theories, it's not just a difference of semantics or terminology. These theories are fundamentally different in the way they work. General relativity is a smooth, continuous theory. We're dealing with, even though the space-time can be curved and convoluted, the theory is smooth, deterministic, and continuous. Quantum theory is the opposite of that. Quantum theory is grainy. It involves quantized energy levels, quantum leaps, if you like, and it's not deterministic. It involves probabilities rather than certainties. So these theories are completely different in character. And Einstein, along with many other physicists in the 20th century, tried to reconcile them, essentially trying to extend relativity. Einstein's approach, given that he developed general relativity, was to extend the theory of gravity to include subatomic phenomena. And he failed in this, and others failed as well. I would say the modern locus of theoretical physics is to go in the other direction, is to subsume general relativity into the quantum theory. And so a quantum theory of gravity, if you like, which is the reconciliation of these two great theories of physics, is going to be quite different from most of the standard physics. The current approaches that are being used, there's an esoteric approach called quantum loop gravity, which essentially tries to get around the continuousness of space and general relativity by saying that space at some point becomes grainy. And so you actually reach a sort of indivisible space unit. So quantum loop gravity is one approach, and the other approach essentially is string theory, or its cousin M theory, which addresses the problem by postulating tiny one-dimensional strings, which are entities that are only manifest at incredibly high energies and incredibly small scales. And then you're forced to pay the price of supposing that there are hidden dimensions, because these theories mathematically all have more than 4 space-time dimensions. They have 8, 9, 10, 11 space-time dimensions, i.e. a lot more space dimensions that we simply can't see. So those are the approaches. And the questioner is right in the sense that black holes tell you that there's a problem. So why do we know, despite having passed all its tests, that general relativity is not a complete theory of nature? The two reasons we know are black holes and the Big Bang. Because in the theory of black holes, there is a singularity. And the singularity is an infinity of gravity. It's a place where the gravity blows up, where you can't calculate. And that tells you something's wrong with your theory. Penrose and Hawking back in the 1970s showed that singularities were an inevitable consequence of general relativity. So it's not just that we don't understand the theory well enough or don't know how to calculate something. It's that when we play the theory out, we predict singularities, and they are nonsensical within the theory, telling us the theory is incomplete. The Big Bang is an even more dramatic example of this situation, when the universe itself was so small that its space-time was curved on the scale of a subatomic particle. And again, you would need a quantum theory of gravity to understand the Big Bang at the instant the universe was created. So we've known for decades that that relativity, general relativity, is an incomplete theory of nature. But and we've been moving, theoretical physics has been moving in the direction of trying to subsume gravity theory into a sort of particle physics framework. But that has not succeeded. It's a very difficult, if it was something that thwarted Einstein in the last 20 years of his life, he's a pretty smart guy. You can imagine this is not easy. And in the 60 years since his death, nobody's figured it out.
The next question is from Tahar, who is on with us live, who asks, you spoke about tidal locking of planetary bodies that are very close to their suns. Does this mean that Mercury and Venus are similarly tidally locked to our sun?
Mercury, yes. Venus, no. So if you're going to look for a tidal locking situation, you would essentially look for the moon that's nearest its planet, and a large planet at that, and you would look for the planet that's nearest its star. And so in the case of Mercury, Mercury is tidally locked. It's on this very rapid 88-day orbit of the sun, at 15% the distance of the Earth from the sun. And so Mercury is tidally locked. The Earth only has one satellite, but if you go into the outer solar system, not each of the gas giant planets, I don't want to misspeak, but there are several moons of gas giant planets that are tidally locked, and it's always the closest moon to those giant planets. So those are always the situations where tidal locking can occur. Now, it doesn't have to occur. I mean, there might be no moon that's big and close to a planet, and there might be no planet that's big and close to its star. So in other solar systems, we don't have to assume that tidal locking always occurs.
Right. Sandra writes in via email and asks, is there any way to know if a planet has been ejected from a star system or fallen into its star?
Yeah, that's a good question, and really we don't know. I mean, theoretically there are various ideas, and observationally these are hard things to say. So planet capture is entirely possible. So the context for this is the fact that stars don't form isolated in space. Starting with the sun and the solar neighborhood, all the evidence is that stars form in groups or clusters. And so if those stars happen to be very close together, their planets may well interact, or those star systems may interact gravitationally, and that can lead to various things. It can lead to planets being ejected, it can lead to planets being tossed inwards and perhaps falling into their star when they're young. All of those things happen in computer simulations. So you sort of have to know the specifics of the situation. In our solar system, it looks, because of the regularity of the orbits of the planets, they're all fairly coplanar, they're all in one plane. Their eccentricities or departures from circular are very small for the most part. It looks like all the planets in the solar system formed together in place, and that probably nothing was ejected, and the only thing that was captured was Pluto, because it's in its oddball orbit. So our solar system appears quite regular, but there are exoplanet systems where the inclination of the exoplanet, that is, the range of inclinations, is so large that it looks like these exoplanets may have been captured. So in our solar system, again, most of the orbits are in one plane, the ecliptic plane, the plane of the Earth's, we see the sun moving across our sky, which is where we see the planets in the night sky. That's not true of all exoplanet systems. We've found exoplanet systems with a range of eccentricities, including polar orbits, and those are very suspicious of having been captured. So there is observational evidence of capture of exoplanets being captured into their orbits. Ejection is harder because we don't know how to see an injected exoplanet. There's a name for these objects. They're called nomads. And in simulations, in theory, really in computer simulations, in many cases, there are ejections of planets early on in the chaotic planet building phase, or when star systems form close to each other, as I mentioned. And so in some of these simulations, nomads happen fairly frequently, not as frequently as normal planets, but not a trivial level. And so if simulations are correct, then we should expect there to be planets like the Earth, or even bigger ones, gas giants, that have been ejected from their star systems early on. And these will be floating through deep interstellar space, and they're called nomads. And essentially we have really no way to detect them, because our primary methods of eclipses and Doppler rely on the indirect effect of the planet on its star. The only technique, with one exception, the only technique that could detect nomads is microlensing. And microlensing is a gravitational amplification caused by the planet passing between us and a more distant, unrelated star. That, in principle, that method could detect nomads, but we don't have enough statistics to make a good limit yet.
Right, the next question is from Jake, who's on with us live. Is celestial navigation important enough to be taught today?
It is still. I've checked out a Navy manual for their if you go to Naval Academy or whatever, there's still a celestial navigation course. It's not as central or pivotal as it used to be in their curriculum. There are various naval training situations, not just in the military, but in civilian life too, merchant marines and so on, and fishing fleets, various things where celestial navigation is important, because while almost every major, boat, from a fishing boat to a destroyer to a recreational vehicle that you might use on a lake or offshore, has GPS now. I mean, essentially your navigation is down to the meter, so you're not even needing to see the stars ever or at all, and you don't need your compass at all, etc. I mean, once you're using GPS, you really, and maybe have sonar to look for things below your boat that might cause you a problem, you don't need celestial navigation. But for sensible reasons, it is still taught, maybe not as much as it used to be. Most serious sailors I know actually had some training in it, or have a book about it, or know the sky, or know their situation, because the technology can fail you, and there are plenty of examples where the technology can fail, or be taken out by lightning, or you just imagine a scenario where you just lose the technology you depend on routinely for sailing a boat. It can happen, and it has happened. So I would say celestial navigation is a dying art, if you like, but it's not completely dead.
The next question is from Tom. Why don't moons in our solar system have their own moons? Do any moons of exoplanets have moons?
That's a good question. So we know that in the modeling of planet and star formation, the planets form in these typically concentric orbits around the star based on its rotation axis. And we see in simulations, and we see in our own solar system, that the moon and planet systems, especially the rich ones like the gas giants, especially Jupiter and Saturn, which each have 60 or 70 moons, and ring systems, of course, that these are just little miniaturized solar systems. And the physics of angular momentum, conservation of energy in how they form is very similar. So the question is, can this happen at a yet smaller scale? And in principle it can, because the physics of these kind of phenomena is multi-scale. The particles out there in space are particles of all different sizes, from microscopic dust grains up to boulders and mountain-sized objects and asteroids and so on. So in principle it could, but in practice we've never seen it. It is, some moons, however, do have orbiting phenomena. So I would say, in a very mild sense, yes, there are examples of this. For instance, Io, moon of Jupiter, a very volcanic moon, has a torus, has a plasma torus. So it has its own torus around it of plasma particles, and includes some rocky particles too. So there are very subtle and mild forms of disk and ring systems, if you like, not always involving particles, sometimes involving ionized gas, but nothing quite as dramatic as moons having moons. We don't tend to see that.
Okay, and I believe we have time for one more question, and this one is from Neil Matthews via email, who asks, the recent discovery of an exoplanet around Proxima b, so close to us, greatly improves the possibility of analyzing an atmosphere for traces of gases that would be life-supporting. At this time, it seems like this is beyond our capabilities. Are there any telescopes that are planned that will make this possible within the next decade?
Yes, there are, and I'm glad to say we're building one. We have 4 out of 7 mirrors made for the GMT, the Giant Magellan Telescope. Is a 25-meter, operationally 25-meter telescope to be constructed in Chile. The Europeans are building a large telescope. Caltech and the University of California plan a large telescope too. And there are some possible space projects that can do this. So the challenge with characterizing the atmosphere of a planet around a star, even one as near as the nearest star system, is the planet is just dwarfed by the starlight. So in this case, where you're dealing with a rather dim star, the planet, to be in a habitable location, is physically very close to the star, and so as seen from afar, it's at an incredibly small angular distance or separation from the star. So the challenge of making this observation is that the reflected light from this Earth-like planet, which of course is a small planet, so it's not reflecting much light. Earth reflects 1 part in a billion of the sun's radiation, is incredibly faint compared to the star, and it's incredibly near the star, especially in this case because it's a dim dwarf star. So to be habitable, that planet has to be much closer to its star than the Earth is to the sun. So that's a double degree of difficulty for any observation like this. However, even with that double degree of difficulty, the answer to the question is yes. With these large new telescopes and adaptive optics, which corrects and cheats the atmosphere and takes you close to the diffraction limit of your large mirrors, in principle, it's possible to isolate the star, to make a model of the response of a telescope to a point spread function, and then suppress the starlight, essentially occult the star, detect that feeble reflected light, maybe as little as 1 part in a billion of the starlight, smear it into a spectrum, and look for the gases that might indicate biology. So the proof of concept of these experiments has been done, in modeling terms, and we're essentially waiting for these telescopes to be constructed. So we can anticipate this experiment being done within about a decade. Thanks very much. Great questions as always. Cosmology to exoplanets and everything in between. We'll be back again in a couple of weeks. Thank you.